So I think that, yeah, we can start the recording. And Marjan, please.
Yeah. Can you see the slides?
Yes, yes.
Okay, yeah, thank you. So I, even though most of you already know me, I leave this slide with my beautiful picture here that was taken on Velika Planina in Slovenia, very nice place, by the way. Here are some of my areas of research. I listed social support networks, also online health-related counseling services, and then local network mechanisms and global network structures. This was my PhD topic. I was interested in how some local network mechanisms like tendency to reciprocate links or tendency to create links to friends of your friend, how these mechanisms affect global network structure. And then I also listed this scientific collaboration. Here we were, this was for, I started this studying of scientific collaboration already at the master program, and I was interested here what patterns of social, of scientific collaboration, co-authorships are formed within different scientific disciplines and how they persist in time. In both this scientific collaboration part, also these local global network structures, I use block modeling to describe the global network structure. And if you go on this webpage, outlier.si, this is my personal webpage, you can find some other things and my papers if you're interested in that. So I already mentioned now block modeling. For those who are not familiar with block modeling, let me just briefly illustrate what is it. As I wrote, with block modeling, we can study the relationships among the units, but there is more. This is actually a clustering approach or set of different methods for reducing large, potentially incoherent, complex networks to smaller structures that are easier to interpret, also easier to visualize. The results of block modeling is on one hand a partition of equivalent unit, so equivalent according to the links, to their links in the network. So if to structure equivalency is very common types of equivalency, and we say that two units are structurally equivalent if they have the same the same links to the others. So they are linked to the same others in the network. So partition with equivalent units is one result of block modeling, and another is an image matrix, which represents the links between and within the obtained clusters. I will also use the term block, which refers to the links between two clusters and within one cluster. Sometimes I will say, I will talk about so-called diagonal blocks. When I say diagonal blocks, then I refer to the links between the units from the same cluster, and the off-diagonal blocks denotes the links between the units from different clusters. Here is one example of a network. You can see that we have these red shaded nodes and these green shaded nodes. And you can see that these red shaded nodes have very similar structural links. They are not linked to each other, but they are quite well linked to those green shaded nodes. And on the other hand, these green shaded nodes have a very similar structure as well. Structure of links. They are linked to each other, and so to each other, to the green nodes, and they are also linked by these red shaded nodes. And because these two groups of nodes have similar structure of links, they can be shrinked they can be shrinked and represented with another node here. And here we have a block model, so another network. And as I said, these shrink nodes are here. So the node in a block model is now a group of nodes from the empirical network. And then we have also the link between this group of nodes or nodes in a group of nodes from empirical network or nodes in block model. And these links visualize the relationships between the groups of nodes. So these red colored nodes are typically linked to these green colored nodes, as is also seen here. And here is a loop which visualizes the fact that those green colored nodes are linked quite well inside the group. But today I will talk about dynamic networks. Here are several definitions for dynamic networks, and we will focus on the networks that are measured at multiple time points. To be more specific, I will talk about snapshot networks. And when we have this type of networks, most of nodes are present at all time points, and the same types of relations are measured. Here's one example, a survey of friendships among high schools. So a survey was done at 3 time points, once in February, then in March, and then in April. So we had 3 time points, and at all time points, we measure the same type of relations, which is a friendship. And we end up with these 3 networks, one observed at each time point. And we can analyze these networks separately, independently on each other. But we could also notice that since these are the same units observed at different time points, these units and links from different time points are not independent. They are dependent. And when this is the case, we can use block modeling of dynamic networks. And the idea is to consider this dependency between the units from different time points. And it is believed that considering this dependency can increase the validity of results, while the aim of block modeling dynamic networks is still the same as in separate block modeling, which is to identify equivalent groups of units and ties among them, and also to identify groups and to study how they change in time. I will provide you with a list of the approaches for dynamic networks. And these approaches, most of them were proposed recently, and they were developed more or less independently. And the idea of this talk will be to identify which approach is the best in which cases, so which one should you use. And to this aim, to answer this question, we will use Monte Carlo simulations, within which we will compare different block modeling approaches. We will also evaluate the sensitivity to the basic network characteristics of these block modeling approaches. And we actually just published the paper, so we already did propose the guidelines for choosing block modeling approaches. And here within this simulation study, we had to consider some things. So if you want to compare the networks, you have to generate networks with different properties. So to consider some factors that might affect the efficiency or efficiency of these block modeling approaches, we consider different characteristics such as network size, block model type, stability of partitions, and so on. And we also wanted to generate these networks in such a way that they would look like real-world networks. We believe that this will increase the validity of our simulation study. And we address this issue by considering some local network mechanisms when generating links within blocks. So the links, when generating the links actually, within or between the groups. And we also had to propose an algorithm for generating networks with a given block model type and a given partition. So you can evaluate the efficiency of a given block modeling approach only if you know what the true solution is. So we had to develop this algorithm. So my presentation will be organized in two parts because we also performed this analysis in two parts. First, we started with directed networks. We considered, as I already explained, several properties. And once we finish with directed networks, we continued with our study on undirected networks. The idea was to generate networks that are similar to so-called co-authorship networks. I already mentioned that this is a part of my research. Scientific collaboration should be, or is it usually symmetric? So we have undirected networks, and if you study scientific collaboration in time, it is very common to see that some researchers leave the network and some new researchers came in. So we also considered incomers and new and outgoers in the second part of our study. So I will talk about this in the second half of my presentation. And these are the approaches that we found and are proposed and can be used for dynamic networks. Not all of them are proposed for analyzing dynamic networks. Some of them are meant to be used for multi-level networks, but we found out that they can be used also for dynamic networks. You can see that we found 8 such approaches, so quite a lot. So if you're a practitioner, you might ask yourself, which one should I use? And this is what we are trying to answer. So we have these 8 approaches, but these 2 approaches, Bayesian stochastic block modeling and a stochastic block model approach for the analysis of multi-level networks, these 2 were not considered in the first part. These one proposed by Peixoto were not considered because we were not aware of this approach. And the second approach for the analysis of multi-level networks was not considered because it was implemented only for 2 time points. It is for multi-level networks, and it was implemented only for 2 levels, which we translate to only 2 time points. So we were not able to use it. But then we meet with this very friendly guy, and we ask him, can you generalize this approach for higher number of levels for time points? And he said, sure. So he published a new version of his R package, and then we were able to use and analyze also his approach. So these 2 are not used in the first, evaluated in the first part of my presentation, and these 2 proposed by Hu and Hiro were not used in the second one, because in the second part we considered newcomers and outgoers, and these 2 approaches are not developed for can consider newcomers and outgoers. So these 2 were used only in the first part of my presentation. So you can see quite a lot of approaches here. Yeah, so directed networks. I mentioned these factors already. We consider different network sizes. When I say small networks, I have in mind networks with 48 nodes, and we also have large networks with 96 nodes. We considered different block densities. We have 2 scenarios, one with low and one with high differences between null and complete block densities. We consider different group stabilities. I will explain this later, but this is about how the nodes change group membership in time, individuals. And then we considered also these mechanisms to make the networks more looking like real-world networks. We have 2 scenarios here, one in which the local network mechanisms are not considered, which means that links are generated completely randomly, and then the one with mechanisms considered, and then we have different block model types. And in all generated networks, we assume that we know the true number of groups, and this was 3 groups. This also can be one of the limitations of our study. And these are now, I will go and explain a little bit more in details these considered factors. I will start with block model types. Here we consider one initial block model type for all scenario. So for all generated networks had this global network structure at the first time point. So we have 3 groups, as I mentioned. 2 groups are very well, the units from 2 groups are very well linked to each other inside the group. And then we have this cluster 3, which is somehow some type of a periphery, some kind of periphery. They are not linked to each other, and they are not linked to anyone in the, from the network. So we have 2 cohesive groups and 1 peripheral group. And then we have 5 scenarios for final block model type. And for block models, this is the global network structure at the end of observations. I ordered these different block model types by complexity. So here nothing changes. So the global network structure at the beginning, at the first observation, is exactly the same as at the end, the last time point. The first and the last time points are exactly the same. Then we have the scenario in which 2 off-diagonal blocks changes. This means that in time, the units from cluster 2 develop links to the units in cluster 1, and also the units in cluster 3 develop links, establish links to the units in cluster 1. Then we have 4 off-diagonal blocks change. Here also the units from cluster 1 establish links to cluster 2 and cluster 3. Then we have 1 off-diagonal and 1 diagonal blocks change. Here you can see that the links within group 2 disappear, and then the links from group 2 to group 1 appear. And then we have 2 off-diagonal and 2 diagonal blocks change. Here, quite a lot. This is very dramatic change in the global network structure, because all within group links disappear. So the groups are not linked to each other internally, and the links from this group 2 and 3 to the group 1 appear. So we have different levels of change of global network structure, organized from the no change to a lot of change. So 5 scenarios for block model type change. Then we have 2 scenarios for block densities. So I said that blocks are about the links within or between the clusters. So I put one example of one network here in a matrix form. We have the units in links, in line, in rows, and the units in columns. So these are the same units. And if there is a dot, this means that a given unit is linked to a given another unit. So this unit, 4th unit, is linked to the 2nd unit. And then we have these blue lines which separate the units from different clusters. And then we have these blocks here. These submatrices are blocks. And diagonal, we have diagonal blocks here. So these are links within clusters, and off-diagonal blocks are links between clusters. And these blocks can have different densities, different amount of links. This is an example of cohesive network. When we have a cohesive network, we ideally have a given number of clusters of units, and the units within groups or clusters are very well linked to each other, and the units from different clusters are not linked to each other. So ideally, we would have a lot of dots here in the diagonal blocks and no dots here in the off-diagonal blocks. we have two scenarios. So when talking about block densities, I'm talking about how many dots, what is the density of these submatrices, how many links are established within or between clusters. So in the cohesive case, we have complete blocks on the diagonal and null blocks in the off diagonal. And when we have the scenario low difference between the density of null and complete blocks, we have the 15% density in complete blocks, this is diagonal blocks, and 5% density in null blocks. And when we have the case with high difference between the density of null and complete blocks, then we have 5% density in null blocks also here, and a higher density in complete blocks, 25%. So you can imagine that in this high difference between the density of null and complete blocks case, here it will be easier to identify groups of units or clusters of units or nodes, whatever. Then we also simulated 4 scenarios for different stabilities of groups. We generated these different stabilities of groups by randomly relocating the units from one cluster into another. We were exchanging 2 units from one cluster into another so that the level of stability did not affect the cluster sizes. So this was fixed. And we have 4 scenarios. Completely stable is the case in which the units doesn't change group membership at all. And then we have a very unstable case in which if we compare the partition for the first time point and for the last time point, they would be completely random. So a lot of units changes group membership. And then we have 2 intermediate states, stable and unstable. In the stable case, if we compare the first and the last time point, we exchange 16% of pairs of nodes, and in unstable case, we exchange 33% of nodes. And then we consider different local network mechanisms because we wanted to generate networks so that they will look like real world networks. We have 2 scenarios for this. One is in which we do not consider local network mechanisms, and then the links are created randomly within blocks, and then another one where we consider these local network mechanisms. And whether the mechanisms are considered or not is reflected with vector theta, which is the vector with the strengths of different mechanisms. So when we consider the mechanisms, all values of vector theta are set to 1, which would mean that all the mechanisms considered has the same strength. But you should know that the mechanisms are not independent. So all what can I say is that they have approximately the same strength. Which mechanisms we considered? Well, we focus on the most commonly analyzed mechanisms in social sciences. The first is mutuality. This is a tendency to reciprocate links. Then we have popularity. Here the units tends to create links to those with the highest in degree, to the most popular units. Then we have transitivity mechanism. This is the tendency to create links to those who are liked by a friend. And then we have these outgoing share partner mechanisms, which is the tendency to create links to those who like the same order. So these are 4 mechanisms, and the strength of these mechanisms is reflected by the vector theta. And this is the algorithm for generating networks. This is iterative algorithm, so we had to set the number of iterations. That the number of iterations was set to 2,500 in our case. And you have to specify some parameters before using this algorithm. This is, of course, the initial network, which can be either a random network, empty network, whatever, just a random network, initial network in the form of a adjacency matrix. Then you have to set the desired partition and desired image matrix with block densities. Then you have to provide mechanisms and their weights. This is this theta. If the values of theta are set to 0, this means that the mechanisms are not considered. If the values of vector theta are different than 0, this means that mechanisms are considered. A number of iterations already mentioned this. And for each iteration, first you randomly choose a unit I, and then you calculate as with the values of the selected local network mechanisms for that unit I. Then you calculate linear combination of the mechanisms. And then you add some randomness, and then considering a unit I, you determine a block B with the highest difference between the current and desired density. And if the difference between the desired and current density is lower than 0, this means that the block is too sparse. And when this is the case, you establish a link to the unit with the weighted network statistics from block B. If the densities, if the difference is higher than 0, this means that the block is too dense. And then you establish a non-link to the unit with the minimum value of the weighted network statistics from block B. But if the density is just right, then you select one option, either to establish a link or not link randomly. And after 2,500 iterations, you return a generated network. We apply this algorithm several times. First, we apply this algorithm on an empty network. Then we got the network for the first time point. We apply this algorithm on the empty network because we wanted that the effect of mechanisms would be seen already at the first time point. And then we apply this algorithm again, but then the initial network, so this initial network was the network from the first time point. And so we end up with the network for the second time point. And then we apply the algorithm again and again. And so we got 4 generated networks, 1 for each time point. Then we apply different block modeling approaches. First, we started with the approaches that were developed for separate block modeling. We used stochastic block modeling and k-means-based block modeling. So this is the case where you analyze the networks from different time points separately, and you do not consider the temporal dependency. So this is what probably most of researchers would do, or at least start at the initial preliminary studies. And then once we run these separate block modeling approaches, we also use these approaches for dynamic networks. We consider different approaches implemented in R or MATLAB, or I forgot to add Python here. But these are all from R or MATLAB, but the one proposed by Peixoto is implemented in Python, but we did not analyze Peixoto's case here, so it's okay. So you can see that we can organize these different block modeling approaches or categorize them in two clusters. You can see that most of them are so-called stochastic block modeling approaches. Here we assume some underlying statistical model, and we estimate this model by maximizing some kind of a likelihood-based measure. And once you get this, once you estimate the model, you can make this statistical inference. While in the case of the deterministic block modeling approaches, we have one representatives here, k-means based algorithm. You apply some iterative algorithm that searches for homogeneous blocks in terms of type values. So you apply some algorithm that is exchanging the nodes between the clusters in a way that minimizing the variability within blocks in the term of type value. So some iterative algorithm, quite deterministic. And then according to how the temporal dimension is considered, the first three approaches are state space models or conditional cluster probabilities models. Here the cluster probabilities or parameter values in a current time point depends on the cluster membership or parameter values at the previous time points. While in these linked and multipartite networks, you have a collection of at least two one-mode networks and at least one two-mode network. And this two-mode network links the same nodes from one-mode network. And in the context of dynamic networks, you apply block modeling block modeling procedure on this joint matrix, but with the restriction that the nodes from different time points cannot be clustered into the same cluster. I have one picture here I will share just to make it more clear. So here we have the example, an example with 1, 2, 3, 4 time points, and we have this one mode networks on the diagonal. So these are the networks that were obtained at each time point. And then we have two mode networks in the off diagonal, and these two mode networks links the same nodes from different time points. So we have values on the diagonal here because the and this means that, for example, these nodes from the first time point is these nodes from the second time point, and so on. And then you apply block modeling procedure on this mega matrix, which combines one mode networks and two mode networks. And the restriction is that you cannot cluster this node and this node into the same cluster because they are from the different time points. And that's it. Actually very easy. What also, so we apply these approaches for dynamic networks twice. First, we use the default initial partitions, and then we also use the manual initial partition, and the manual initial partition was taken from these separate block modeling approaches. So we run this stochastic block modeling approach for on each time point separately, and we take and we use this partition in the for example this Matthias and Miller approach as an initial partition. So we believe that if you use this result from the separate block modeling approach as an initial and as a starting point in this dynamic networks approach, then this dynamic networks approach might give you a better result because you will help him somehow he will have a better starting point when looking for better partitions. So each approach produces two sets of results. So each of these approach produces two sets of results, one with manual and one with default initial partition. And we were further analyzing the one with the best This can be either minimum or maximum value of the optimized criterion. And to quantify the efficiency of a given block modeling approach, we calculated the adjusted rand index between the true partition and the one that was estimated by using these dynamic block modeling approaches. So this was calculated for each time point, and we were further analyzing the mean value of ARI across all time points. For those who are not familiar with the adjusted rand index, this is defined as the proportion of all possible pairs that are in the same cluster and all possible pairs in different clusters in both partitions. So if you have two clustering results and if they are very similar or exactly the same, you will get the value of 1. But if they are very different, then the value will be lower. And this ARI allows us to compare the similarity of partitions that are obtained on different networks, different sizes, and also number of clusters, although the number of clusters here was fixed. So the perfect fit, when we have two partitions that are the same, you get 1. And when you have when you compare two random partitions, the expected value would be 0. In some cases, you can get slightly negative values, but the expected values would be 0 if you have two random and independent partitions. So we want high values of ARI, because this would mean that the partition obtained with this block modeling procedure will be very similar to the true partition. So high values of ARI are desired. I try to summarize these mean values of ARI considering the network size and the block density difference. These are the two factors that had the very high effect on the results. We have on x-axis, we have block model type change. On y-axis, we have mean ARI, and in rows, we have the change of the block density difference, and in columns, we have different network sizes, small network and large network. And if we focus now on small networks with low density difference between complete and null blocks, you can see that ARI values are very low, which means that the problem was too difficult for most approaches. But if you focus on large networks with high block density difference, you will notice that the values are very high, which means that the problem was too easy for most approaches. So we will focus on these two cases. So one is when you have large network and low block density difference, and one is when you have small networks and high block density difference. In both cases, you can see that in general, dynamic stochastic block modeling approach is the best when the block model type does not change in time. But if the block model type does change in time, stochastic block modeling for multipartite networks produces the best result. So this is kind of main result here. But we can also take a look at some details. If we focus on large networks with high density difference here, you can see that I also added, so the results are organized a little bit differently now. We have this group stability on y-axis and mean ARI on y-axis. And then in rows, we have the case in the first row is the case in which we considered mechanisms. So this is more a realistic case probably. And in the second row, we have a random case. So when the links within blocks, or this means the links between and within clusters, are randomly generated. And then we have this in columns, different block model type, changes of block model type. So what you can see is that all approaches works better when the links within blocks are randomly generated. So when there is no mechanisms, I can guess that this is because when the mechanisms are present, some local substructures within blocks can emerge, and this can then lower the efficiency of these block modeling approaches. All approaches provides excellent results when block model type does not change. So this is this case. Mean R is almost 1. But if block model type does change, then this stochastic block modeling for multipartite networks, this is this red, produces quite good results. And stochastic block modeling for linked networks produces, which one is this? Multipartite networks is this, and linked networks is this. But what you can also see is that it's not that seen here. For example, here, when the global network structure changes a lot, then the efficiency of block modeling approaches is lower. And also the stability of groups has a stronger effect on the efficiency of these different block modeling approaches. But if we do use these separate block modeling approaches, so when we do not consider temporal dependency, you can see that, so these are these 2 lines here, that the shapes are not filled with color. So these 2 black lines, you can see that they are not affected with the stability of groups. However, in average, the results are, the mean area are quite lower, which means that it makes sense to use these dynamic networks approaches, approaches for dynamic networks also here. This is the case with small networks and high density difference. RE values are a little bit lower, but overall the message is very similar. And these are large networks and low density difference. Also very similar conclusions can be made here. But the RE values are quite lower. So if I conclude, network size, block model type, stability of partitions in time, local network mechanisms, all these factors affect the efficiency of different block modeling approaches for temporal networks. It is worth considering these approaches for temporal networks instead of approaches for analyzing networks for separate networks, separate from different time points. However, it was a little bit surprising for us that, for example, these approaches that were not developed for primarily for these dynamic networks works very well also on these dynamic networks. Here are 2 most effective approaches that are suggested. The first is the one is stochastic block modeling for multipartite networks. So you can see this approach was developed for multipartite networks, not for dynamic networks, and yet it is the best approach, one of the best approaches for dynamic networks as well. So this is what I was talking about. And this block modeling approach should be used when block model type does not change. While if the block model type does change, then dynamic stochastic block model should be preferred. I forgot to mention that this stochastic block modeling approach for multipartite networks does not converge in some cases. So this is this approach, and you can see that we use different sizes of these dots to visualize the convergence. So this is the proportion of converged cases, and you can see that in some cases this approach really have some convergence issues, but it's not very common. I mean, node sizes are very different here, but consider the values here. This is here the proportion of converged cases is 97.5%. So it's from time to time this block modeling approach have some difficulties with convergence. It's not that critical, but it happens from time to time. So these conclusions are also published in social networks. So if you are interested, you can follow this. It's not linked, but it's title, and you can read this for more details. I already mentioned at the beginning that there are some limitations with this research, and this is that the simulations were done only for asymmetric networks and without incomers and outgoers. So in the second part of our project, we focused on undirected networks. So we got the inspiration from the empirical co-authorship networks. So in the past, we apply block modeling procedure on the co-authorship networks for all scientific disciplines, 72 scientific disciplines for 2 time points. First from 1991 to 2000, and the second from 2001 to 2010. Then we were studying how this global network structure changes in time. So whether scientific collaborations are very stable or time or not. So a couple of years later, we got some new result, some new data. So we had the data by 2020, 10 years more. So we could form 3 time points, 10 years long. And we were asking ourselves, what if we would apply block modeling procedure again? And what if, how considering this temporal dependency would affect the results? So also which of this approach should be used? And there are some characteristics of these co-authorship networks, and obviously symmetric ties, and newcomers and outgoers. It turns out that there is quite a large percentage of these newcomers and outgoers, and relatively unstable clusters. However, the global network structure, so the block model type, remain quite stable in time. So this is something that we can consider when choosing between different block modeling approaches. So we know that the global network structure remains quite stable in time. Okay, we repeat our simulation study. So network size, 2 scenarios, the same as in the previous case. Group stabilities, the same as in the previous case. 3 groups also here. And some changes are in the mechanisms and block model types, and also in incomers and outgoers. So we considered 4 scenarios for incomers and outgoers. The 2 are without incomers. I will say, so this is the reference, no incomers, no outgoers. Then we have one in which we have 0 incomers, but 20% of outgoers. Then we have another one with 20 incomers and 20 outgoers. You can see that if we have 20% of incomers and 20% of outgoers, this does not change the network size. But if we have outgoers, the network size will decrease. And then we have the less scenario with 20% incomers, which will increase also the network size. When incomers joined to the network, they came in without any links to the others, and a group to which they join is determined with probability that is proportional to its size. So if larger groups has larger probabilities that they will get new coworkers. So this is probably quite realistic for co-authorship networks or research teams, for example. Because they have more money, they can hire new employees. And all the units have the same probability to leave the network, but here are two exceptions, because we didn't want to have two small groups. No one from a group does leave the network if the a group consists of 5 units or less, and incomers cannot leave the network. Incomers cannot be also the outgoers within the same time period. We considered the mechanisms also here. At times we have symmetric links. The number of possible mechanisms is limited, so we focused on 3 types of the mechanisms: popularity, assortativity. Assortativity is the tendency to create links to those with similar in degree. So while if here you will prefer to link to those that are very popular, here in assortativity case you will prefer to link to those that are of the same popularity level as you are. And then the transitivity, as said, this is the tendency to create links to those who are liked by a friend. Yeah, and then we have different block model types also here, but the number of possible block model types is also limited because of symmetric links. So initial block model type is very similar as in the previous, in the first part of my presentation, but here we have symmetric links. So 2 cohesive groups and 1 peripheral group. And then we have 3 scenarios for final global network structure. In the first case, nothing changes, so the global network structure remains unchanged. And then we have 2 changes. You can see that the links between group 1 and 2 and 1 and 3 appears. And then we have this scenario C, in which 1 diagonal and 1 of diagonal blocks change. So the links within blocks within group 2 disappear, and the links between group 1 and 2 appears. And this is the algorithm for generating networks. It's very similar as before, but here you also have to set the number of incomers and outgoers, and also the minimum cluster size. So this means that if the minimum cluster size is set to 5, as in our case, this would mean that if a given group has only 5 individuals, then no one will leave the group. So this is why we have to set the minimum cluster size. And then everything is the same. So we randomly choose a unit I within each iteration. Then we calculate S with the values of selected local network mechanisms for this unit I. Then we calculate a linear combination of the mechanisms. Then we add some randomness. And then considering unit I, we determine a block B with the highest difference between the current and desired density. And then this, if the block is too sparse, if the block is too dense, then a given unit will decide to establish a non-link to the unit with the minimum value of the weighted network statistics from block B. If the density is just okay, the unit will randomly choose one or another option, so to establish a non-link or to propose a link. So, and here is the difference between this algorithm for symmetric networks and the previous one. Here, instead of just creating a link to a unit J, a unit with the maximum value, the weighted network statistics from block V will be denoted as a unit J, and this unit J will consider all other units in terms of whether she or he wants to create a link link to them or not. And then we basically calculate this weighted network statistics from unit J to all other units in the network, and then with probability proportional to this weighted network statistic, given unit J will confirm incoming tie with unit I, and then the symmetric link will be formed. And then we, at the end of each iteration, we consider whether to add some incomers or outgoers. And after many iterations, we return generated networks. So the only difference with the previous algorithm is that when a unit J, unit I decides to create a link to unit J, a unit J will decide whether confirm or not the incoming tie. If unit J decides to confirm the link, then a non-directed link will be formed. We apply this algorithm 3 times, as in the previous case. Now we have only 3 time points, not 4, because quota ship networks for Slovenian case. And then we apply these separate block modeling approaches as before. Here we considered also this Peixoto. So this algorithm can be used on dynamic networks and also separate as a separate block modeling approach for if the networks are considered observed in only 1 time point. And then we also apply these approaches for dynamic networks. Now we have this Schaeberle-Liddell and Peixoto approach also here. This Schaeberle-Liddell is very similar to dynamic stochastic block modeling by Matthias and Mille, which was the best in the first part of my presentation is if a block model type does not change. So this Schaeberle-Liddell is conceptually very similar to this dynamic stochastic block modeling proposed by Matthias and Mille, but does not have limitations, some limitations. For example, the number of groups is not fixed for all time points, and also the diagonal blocks can change in time. Because this dynamic stochastic block modeling approach proposed by Matthias and Mille have this assumption that the diagonal blocks should not change from null. The density of these diagonal blocks should not change in time. But this is not the assumption anymore for Schaeberle-Liddell. And also the assumption of Matthias and Mille is that the number of clusters is the same in all time points. But this did not affect our simulations because we assumed that we had 3 clusters in all time points. And this is just a fun fact that Peixoto assumes Poisson distribution of links, and this works very well, especially when we have sparse networks. Then we run these algorithms twice, first with a default initial partition and then with initial partition obtained from separate block modeling, and then we keep the so for each approach for dynamic networks we obtain 2 sets of results, and we keep and further analyze the one with the best value of the optimized criterion function. This is all the same as before, and then we apply this adjusted trend index to compare the true partition and the one obtained with these approaches for dynamic networks for each time point. And we calculated the mean area over all time points, and we further interpret this. And here are the results. So first we focused on small networks with mechanisms. Yeah, I also have random case, but I started with mechanisms because we believe that this case is more realistic for social sciences. So small networks, 48 nodes, and the mechanisms. In rows we have how much the global network structure, block model type changes, no change in block model type, some change, a lot of change. And then by columns, we have how many incomers and outgoers we have. Here is a reference, no incomers, no outgoers. And on the left hand side, we have 20 incomers, 20 outgoers. So then the final network size is the same in these two cases. And yet you can see that the area values, which are on y-axis, are a little bit lower when we have some incomers compared to and outgoers compared to when we have no incomers and outgoers. And on y-axis, we have the stability of partitions from completely stable to very unstable. What else should I say? Yeah, if you focus on the rows, so block model type changes, you can see that the area values are generally decreasing from no change in block model type global network structure to a lot of change. And here you cannot see much difference if the partition is completely stable or very unstable. However, there are some exceptions. For example, these ones, stochastic block modeling for multi-level networks. It seems that this approach is not that robust for when we have some incomers and for the case when the partition is not so stable. So when the units change the cluster membership. However, I also prepare this table that you see here, kind of general recommendation. So if block model types does not change, and if you have no incomers, use dynamic stochastic block modeling. So no change in the block model, first row, and this column, no incomers and outgoers. You can see this yellow method is the best, regardless of whether you have incomers or and outgoers or not. So in all cases, this yellow line is the best. So this is dynamic stochastic block modeling proposed by Matthias and Wille. However, if block model type does change, so these are these two rows, and if you have some incomers, if you don't have incomers, so this is this blue line, you can see that this stochastic block modeling for multi-level networks is quite okay. If you have incomers and outgoers, this stochastic block modeling for multipartite networks works quite well. The same results are when you have large networks and mechanisms. And when you have small networks and random case, there are some differences. So if the partitions are stable, so this is the first value on x-axis. If you have stable partitions, and if block model type does not change, so first row, and if you have if you don't have incomers and outgoers, then this dynamic stochastic block modeling approach is quite good. And if you have unstable partitions, so this is this part here, also this k-means for link networks works quite well. And if the block model types does change, then stochastic block modeling for multi-level networks is quite well performed. if the partitions are stable. Otherwise, k-means block modeling for linked networks is quite efficient. But if you have large networks and if the links are assumed to be, if the links are randomly generated within and between the clusters, then the best approach is dynamic stochastic block modeling if block model types does not change. But if block model type does change, then this stochastic block modeling for linked networks is the best. I try to somehow with these tables to simplify things, but I think it still looks quite complicated. So I created yet another slide with recommendations. This is in blur because we are still working on the paper. It's not yet published. It's not yet written, but it will be in a few weeks. So these are my recommendations. So the most worth considering approaches are stochastic block modeling for multi-level networks. This is a very safe choice when there are no incomers and outgoers. Stochastic block modeling for multipartite networks is a safe choice when there are incomers and outgoers. But this from time to time have convergence issues, not always, very rarely, but it can happen. K-means block modeling for linked networks proposed by Ljubljana is very effective, but it can be outperformed by other approaches. So you are safe to go with this approach, but you could get better results with some other approach. But if you can assume that the links are randomly established within blocks, within clusters, then this is the approach. And especially if you have large networks. Dynamic stochastic block modeling, the one proposed by Matthias and Mille, works very well if the block model type does not change. However, it has relatively poor, compared to the others, performance if the block model type change and if the network is large. Now, this dynamic stochastic block modeling approach works very, so this is this one, works very well also if the network is large. It's not that it's poorer if the network is larger, but other approaches became more effective with a larger network size. So just a disclaimer. Now in the future, we will apply and evaluate this block modeling approach on real world co-authorship networks. My colleague is already working on this. And he's also trying to use different approaches and compare them, considering the substantial knowledge about the collaboration networks in our case. And more general conclusions, always use prior knowledge and run separate analysis when you start with your network analysis. Then try different initial partitions. For example, use the default initial partition that is already, when you run your R script, the functions has some default values for initial partition. So just use this, but also try to first analyze each time point separately and use this result as an initial partition for the dynamic block modeling approach. This can increase the efficiency of these block modeling approaches in some cases. And yeah, these are the best block modeling approaches: dynamic stochastic block modeling for multi-level networks, and stochastic block modeling for multipartite networks. Use dynamic stochastic block modeling for stable network structures. Otherwise, consider stochastic block modeling for multi-level networks when you have no incomers and outgoers, but if you have some incomers and outgoers, consider stochastic block modeling for multipartite networks. So these recommendations is, I try to make it easy. So I was looking at the first simulations results and the less simulations results, and these are the I think the most safe approaches to use. They're not always the best, but these are approaches with which you will not have very poor results. You do not have a lot that you don't risk a lot if you use these approaches. So in some specific cases, some other approaches might be better, but sometimes when you are analyzing real-world networks, you don't really know whether all these assumptions are satisfied or not. And yeah, from this perspective, these are the most are the safest to use. Maybe I can take a look if there is some example. I forgot. I will not remember. I was looking at these pictures for hours, and I forgot. I'm looking for example in which you could do some harm. No, I will not spend your time. Yeah, that's it. That's all what I prepared for today. Sometimes I'm explaining things a little bit confused. So if you didn't understand some things, feel free to ask and I will be happy to clarify and explain. Or if you have some suggestions, or if you try to use these approaches before, if you have some experiences, you can share them with us.
Dear colleagues, do you have any questions and comments?
Well, I have a small question.
Yes, please, Anna.
For your presentation, it was really great to see these really practical and useful results. So I have a question about your experience. So what do you think is the most convenient software to do this stochastic block modeling, and what were the main obstacles that you faced?
Yeah, let me go to the just. Now, Peixoto, his approach is implemented in Python, but if you're, and also it works, I think, only on Linux. I'm not completely sure, but I think that his library works only on Linux. And because we were using R, we had to write some scripts and so on. And I am also a user of R. So this is not convenient from this perspective. Then there is another approach. I think that these two approaches, Hero, but I forgot. I'm not quite sure. But I think that these two approaches are written from MATLAB. And so if you are familiar with MATLAB, you can use these approaches. But other approaches are very easy to use and very convenient. So, but these were not at the top. I mean, they're not always the worst, but they're not the best. So I will stick with these approaches, and these are quite well implemented in R, very easy to use and very user-friendly.
Great, thanks. And so did you develop the general approach for the Bayesian stochastic block modeling?
Sorry?
And did you develop this like general approach to use this Bayesian stochastic and get this result?
Sorry, I didn't hear you properly. For the first part of the question?
Yes, so you told that you like got many problems with this Bayesian stochastic block modeling, and you used Python and Linux. So what was your solution for this problem?
Yeah, the problem, I mean, you know, this practical my solution was to write R scripts that were able to call MATLAB and run functions in MATLAB. So we called the MATLAB from R.
Okay. Okay,
This
got
is what we, yeah.
Okay, thanks.
But we could also, I mean, we wanted to call everything from R because then we hire these web services for computing, yeah, but otherwise you could just use MATLAB, and if you're familiar with MATLAB, there would not be such problems. Yeah. There's some other difficulties with this. I mean, I think these two approaches, but I forgot it was related for calculating criterion function or something like that, but I really don't remember the details. Yeah. There is a question if we want to plan in the future to consider more factors that may influence the researcher's choice, or particular, for example, a limitation of missing values, outliers. Not in the near future. For this project, we promised these factors. So we will probably end here for at least for some time, and we will focus on analyzing real-world networks. But maybe later, if we will apply for another project, we will consider some other factors. Yeah, we started with the most common factors, but maybe if you're interested, maybe you can continue our research from here. Maybe some new approaches will emerge as well. Maybe once we present our results, maybe some researchers will be able to identify where their approaches are not that efficient, and maybe they will try to improve and then we will have to repeat everything. Yeah. But yeah, the answer is not for now.
Okay, Marjan, I also have a question. So first of all, thank you very much for this presentation. I think this is really a great example of research. Personally, I really like these cases of structuring of some knowledge, because when you have a lot of different algorithms, so you really sometimes just don't understand which one to choose. And I think that this is really important job for the field, because someone really needs to make some reflections about what are the algorithms and which algorithm is better to use. And probably, of course, if we didn't use this methodology so much before, so probably it really looks a little bit complicated. But I think this is kind of a nice starting point to go somewhere deeper. So, for example, now we just finished the project devoted to the collaboration networks of Russian sociologists. And it looks like we do have, so this is a dynamic network, because we have 12 years of observations. And it looks like we could use some of these algorithms to analyze this network. And considering this, like practical usage of some algorithms, my question would be, so if we do not know yet if there are outgoers and incomers, and we do not have the understanding of how the network was changing, so should we, which kind of the prior analysis we should make before using some like very developed algorithm?
Yeah. So this I created. So here we considered many factors, and I decided to create the table, this one, with only whether block model type does change or not, and whether you have incomers and outgoers. This doesn't mean that these two factors are the most influenced. They are actually very influential, but I choose to create this table based on these two factors because they are the easiest to identify. So whether you have incomers and outgoers or not can be checked by looking at the list of all the units from different time points. And if the list is changing, then this means that you have some incomers and outgoers. So this is checked. This is more tricky, whether block model types does change or not. Here, you can first run separate block modeling. So analyze each time point separately. And then look at the resulting block model structure. If the block model network structure, if the block model type is very similar at all time points, then you can assume that block model type does not change. As you have to put, so especially the diagonal blocks are usually the most critical ones. Whether the links within the groups are disappearing or appearing or not. So yeah, maybe run separate analysis to get a feeling. If the block model types are changing a lot, then probably you cannot assume that it is stable. But if it is not changing, then you can use this. Another approach would be to use, for example, here you have dynamic stochastic block modeling for link networks. One assume that block model type does not change. One assume that the block model type does change. You can run them both, and if you will get the same results, that would mean that block model type does not change. Otherwise, it would mean that it does.
Mm-hmm.
No, sorry. Don't consider this suggestion. It's a wrong suggestion. Because no, it's okay suggestion, yeah. At least in this case. But in this case, no, don't consider this suggestion. Just apply separate block modeling approach and then analyze these results, and based on this, decide whether block model type does change or not.
Mm-hmm. Mm-hmm. And thank you so much. And then probably one more practical question. So when you're talking about large networks, what is the size of these large networks?
Here is 96.
96?
Yeah.
Nodes?
Yes.
96 nodes. Okay, and then I'm sorry, I have another question. So, and if you have a huge network of collaboration, so what would you propose to do? So it would be like 20,000 of nodes in the network.
20,000.
Mm-hmm.
Then I'm afraid.
So should you somehow extract the main group and then to look inside this main group?
Yeah, if you have these main components, then this would be one approach, yes. But if you don't have main components, or if you cannot, it's when you have such large network, it's very, you have to identify regions of networks and analyze them separately. But the general approach for larger networks is that this algorithm proposed by Peixoto is extremely fast. Then maybe consider this one. Stochastic block modeling for linked networks. So large networks it's not that bad approach. I mean, because it's very, you have some incomers here, but this approach is very fast, and this is one advantage of this approach. Yeah, but if you have a very large network, analyze some subnetworks separately, and because this is the only way. All these approaches, I mean, in general, these approaches are quite slow, especially this approach. I forgot a little bit, but so Peixoto is fast. Giverna approaches are quite slow. Matthias and Mila is something in the middle, and Marjan also. Yeah. I mean, in general, are not that fast, even for 96 nodes. Yeah. Yeah, for 20,000, or even 2,000 or 1,000 nodes, yeah, you should identify main components or some other, in some other way, different regions of the network, different parts.
Okay, thank you so much.
Maybe you have a lot of, if this is collaboration networks, usually you have a lot of small groups and also many twins, subnetworks of size 2 or 3, and then you can easily identify such without using any algorithm, and that with such approach you can drastically reduce the size of a network for block modeling.
Okay,
but you also have to, since you have several time points, it become a little bit different. Difficult, yes.
Yeah.
I mean, difficult in the sense that this subnetwork will grow as you are adding time points.
Yes, yes. Okay, we will think how to implement it. Thank you.
Ilya is asking for.
We had one more question, yes, from Ilya.
Template. There, I will give me 1 minute. I will give you the name of a template. I'm not allowed to. I buy this. I bought this. I'm not allowed to. Just a second. Yeah. Montagua. This is the name of the template. You will, it's without this backslash. You will find it online.
Thank you very much.
You're welcome.
Yeah. Okay. Thank you so much, Marjan.